Hello?
Hello.
Hey, Gordon. I'll just set this up and be there.
Hey, Dr. Shardish. Do you hear me? Oh, I think so. Hey, Wahid, how's it going?
It's okay.
You get the I don't think I talked to you about the last homework. If you didn't get it finished up, you can text me if you need to. I know we haven't talked for a little bit, so.
Okay. I have one quick question for physics 430. Did he mention anything about a test coming up?
No, he hasn't, but there is a quiz due on Friday.
Okay.
Or quantum.
Yes.
Yeah, I checked the syllabus. I think we do have a test this coming Monday, but it's a take home.
Okay. That's what I thought.
Glad you checked that. I hadn't seen that.
Yeah, I knew there was a test Monday. I just wasn't sure how it was.
Do you know if he'll give the week for the take-home test or just till the next class period?
Not sure. Yeah, I'm honestly not sure. I'll ask him later today.
Okay, yeah, I'm sure he'll probably say something on it on Friday anyways, but
Hello? Can someone speak something?
Hello?
Oh, yeah. Thanks.
Hello.
Thank you. JK. So you guys are talking about the exam. We need to talk about the exam for this course also, right? That's on Friday. So the exam is, I decided that it will be take home exam. And I will post it sometime on Friday, and it will be due on Monday before the class. So just Does that sound reasonable?
Yeah.
So it will be very homework type. And, I'll also use it to cover some topics, like the typical homework that I do. So basically what I'm planning to do is treat one of the homework as a midterm. Usually I give it as a homework, I'll give it as a midterm. That's what I'm planning to do. But I'll surely add a couple of questions which are assessment based. Okay. That's the what I have. I do notice that I've not graded the homeworks as of now. A couple of them, usually they are graded by now. So I'll try to get that done today evening. It shouldn't take too much time to do that, and that should be available. So look for it. So the usual detailed feedback. Okay. Anything else? Christian, you wanted to say something earlier?
Oh yeah, I can just talk to you after class for a second. It was just about the Mathematica program.
Oh, okay. Yeah, we can talk that after. Okay. So,
Professor, sorry, I joined just a minute late. I caught the end of what you were saying about the midterm. I just wanted to be sure on exactly what we're doing with the midterm.
sure. Yeah, let me write it down. Yeah. So homework 3 was due today, right? It was due actually on Friday. It kept postponing, and it was due today. So only thing pending now is midterm 1. So midterm 1 will be take home. So it will be available by Friday, maybe even before. It depends on when I work on it. And due on Monday. Very homework based, like it. It's like a homework, but it will be weighted like a midterm. Did I clarify that, Travis?
Yeah. So just take home, that's the only difference. And then are you gonna have the the homeworks like graded before this weekend then, or?
Yes, homework I will grade it by evening today. I
Okay,
realized
great.
only in the early morning today that I have graded it. So hopefully by end of the day today. Okay, I'll try to do it.
Awesome. Thank you so much.
I can do it. I miss it. If you don't see it done by the end of the day today, so feel free to write me email and remind me. Usually doesn't take too much time. Okay. And that actually raises the question of the class on Friday. And do you think it's fair enough to have a class? Or?
Dr. Shajesh, do you have the mic on?
Oh, no. Oh, not. It's not. Good. Jeremy, you should remind me. Okay, let me put that on. Hopefully. So it really gets bad, huh? Fine.
It's much better with the mic. Yeah.
Hello? Okay. Hopefully it's better.
Yeah. Thank you.
Okay. I was saying, I can actually even remove my mask today because I'm the only one in the classroom. So maybe that will make it better, slightly better too. The camera is here, yeah. So what was it? I was saying about the class. I typically don't like to take extra classes or anything. So I'm hesitant. So we are not very far behind either. It's just that we missed one class on Monday, I think. So do you want to have an extra class, or you just want to relax for the, get ready for the exam? So I'll leave it to you guys.
I honestly don't mind either way.
Okay, so that doesn't count. Anyone thinks that, feel free to say, because I typically don't like to have extra classes. So
I mean, if we don't need one, then I'm fine with not having one.
okay, so there you go. So let's not have it. Okay.
Yeah, I agree. The only thing is if there was ever like, if we had like an extra to do like a review over some of the material, just kind of like do more examples, maybe like that would be cool every once in a while. If it
Oh,
was
so
like, just
you
like
would
an
like to have a review session on Friday? Is that the suggestion?
not necessarily like if we need it, but like it'd be nice kind of just to kind of go over some of the even like the more recent material that might be on the exam as well.
Okay.
This is like a kind of like recap.
Is that take home? So I'm not sure how it works.
No, that's fair. I mean, even like so, like if you were to upload it after the class, then that way we wouldn't be able to ask questions off of the homework or off of the exam. We would only be able to ask stuff that like we've done in class per se.
How about this? I will post the homework before Friday, and you're allowed to ask about the exam during the class. You don't
Okay.
have to come. Okay. I typically make that available even otherwise, that you can ask questions about the exam to me. In fact, at some graduate level, I even encourage talking about it. But let's keep it a little like it's open resource. Remember.
Yeah.
So even a little bit of consultation is fine. Just don't get together and work on a table and submit one piece. Yeah. So treat it like a homework. How about that? Yeah. Yes, Christian.
You said that we weren't that far behind, but is there anything that we're gonna have to like sacrifice, I guess, that we won't be able to cover by not having a class?
Okay. Now, typically what happens is that there is scattering that like it is all shortened. You can keep doing this aspect as you want. As far as the curriculum goes, I think we do cover reasonably well. Now it's a question of how much in detail. Like you can do scattering in a month, and you can do it in a week, right?
Well, yeah, if it's more scattering based, then I guess I had some experience with that with you anyways. So that's yeah, I don't.
Yeah, so let's see. As of now, I feel that we might be able to do whatever we want to. It's just a matter of how much. And again, I've noticed that since this is a undergraduate E&M, students who don't want to see it in too much detail either, because then I assess you guys on that. And that also is a challenge. So yeah, I don't know.
I was just wondering if there was anything.
That's a good point, yeah. But how about this? We won't have a class on Fridays based on at least one vote or two votes, right? But if necessary, allow me to at least have a recording at the end. Like I can ask you guys to look into, like I can record a lecture and send it to you guys, and that can act like a class if necessary. I won't use it. I won't misuse that unless necessary. Is that reasonable? Okay, I won't force you guys into listening to many lectures, right? Okay. So let's. So about the class on Friday, there will be exam posted, and I will be available in the classroom as an office hours kind of thing, and anyone can come and talk to me during the time. It won't be recorded. Okay. Or do you guys want it to be recorded?
I don't really. I mean, it doesn't matter to me.
Yeah, I didn't. Yeah, no one said anything, right? Yeah. Okay. We'll see. I'll think about it. Yeah. If there is anything substantial, we can record it. Otherwise, we leave it alone. Yeah. Okay. We want to. We started on talking about the magnetic field and magnetic vector potential due to a circular wire, and so here is a question for you guys. What is, so we do know that there is no North Pole and a South Pole, correct? So if you do want to make a magnet, how would you make one? How would you go about building a magnet artificially, not the naturally occurring?
Like a electromagnet?
Yeah, electromagnet, good. And what do you do in an electromagnet?
You just run current in a loop, basically.
Current in a loop, right? So that leads to the idea that there is a circular loop in that. So it seems like a circular loop is the basic element for a magnet. And a magnet itself, because there is no North Pole and no South Pole, is the first property that defines it is a magnetic dipole moment. Okay, so we are going to define what is called a magnetic dipole moment. And what is a magnetic dipole moment?
So the
From your
direction,
elementary or introductory courses?
oh, like what's the expression for it?
Yeah, what's the definition of magnetic
Um,
dipole moment?
So electric dipole is obviously based on the charge and the distance between the charges.
Yes.
The direction of the moment will point in the direction that the dipole would align with.
So
in the present.
electric dipole moment, so let's remind ourselves, is P is equal to Q charge times the distance, the vectorial distance between the negative charge and the positive charge. So there's a negative charge and a positive charge, and it doesn't have to be equidistant, equal charges, but the basic idea is got from there. That's your vector A. Notice it goes from negative to positive, correct? That's your electric dipole moment, and you can make this smaller and smaller if you want. That's perfectly fine. That's the basic idea. What is magnetic dipole moment from your introductory physics? What's a definition? Any memories? Right. Not at all. Okay, so it is a magnetic dipole moment. So this is a magnetic dipole moment now. Is equal to, so we'll call it M. And it has a direction, of course. I will talk about the direction. And it is talked about for any loop of current carrying wire, right? Let's keep it flat for the moment. So that's I in it. And that is an area associated with this loop, right? You can say that what happens to the area if it is not in a plane. We'll talk about that. So, so the magnetic dipole moment will be current times the area. Right? So where A is the area. Familiar? Have you heard this? Seen this before? Should have. Okay. No?
I don't think so.
Okay, surprised. But yeah, so, I mean, it was there in the introductory level, but maybe it was not stressed too much, but that's okay. Okay, but what about the
vector. What do you think will be the vector there?
Normal to the area, or like the area vector, basically.
Yes. So the moment you have area has a vector nature to it, in the sense if this is a plane, it's perpendicular to that. And the moment you say perpendicular to a plane, there are two of them, right? You can come out of it or you can go into it. Then the right-handedness of the current comes in. So you have to use your right hand to curl your fingers in the direction of the current, and the thumb gives you the direction of the dipole moment. So for example, for this loop of wire, the magnetic dipole moment is into the board, and similarly, so this would be, oh, sorry, that way. So this will be, so in this case, magnetic dipole moment is going into the board here. Here, the magnetic dipole moment is coming out of the board. Okay. You might wonder, oh, what about if it's a more complicated geometry? Then you can always break it into smaller loops. So let's say, so think of a loop like this. Right. So this is perpendicular to each other. Is that clear? So this is in one plane and the other one is in the other plane, and you say, okay, what is the area vector associated with this? That's not very obvious. What is the direction of the area there? But what you can do is you can break this into two loops in the following way. Draw a temporary imaginary line there. Think of that as a current. And in one way, this is going in the loop that will cover the bottom loop, and the opposite direction current travels in the other wire. So in such a way that these two cancel out. Is that clear? So this can be broken into two loops. One is having a magnetic dipole moment in this way. So that's your magnetic dipole moment M1. And this one will be having a magnetic moment M2. So the total magnetic moment will be M1 plus M2. Okay, vectorially you have to add. Okay, so that's one way of defining a magnetic dipole moment. But we can also talk about magnetic dipole moment of a single point charge. Right. So let's think of a positive charge Q moving with velocity V. Right. That's a path of the charge, and that is a single point charge. And remember that if there is a moving charge, there is a current associated with that. Correct. So that gives you the idea that there is a current here. But what is the area associated with a moving point charge? So how do we associate a magnetic dipole moment? So let's simplify this. Instead of a complicated trajectory, let's have a circular trajectory, and we will do this for a circular trajectory and then come back and generalize this for a arbitrary charge. So let's say there is a point charge plus moving with velocity v in along a circle of radius r. Correct. So we do know that magnetic dipole moment for a circular wire will be I times A. So let's say this is n hat times I. I is a single charge. It is going in a circle. So you have Q over the time period T, right? How much time it takes to go around the circle once, that's your current. So let me do this in two pieces. So that's I times A. So that's equal to n hat times charge q over the time period t. And the area is pi r square. Right. And let me write this as q times, or 1/2 times q times 2 pi r over t, and there is an r itself, and there is an n hat. 2 pi r over t is like the velocity in a circular motion. So that's n hat times 1/2 times q times v and a r. Notice n hat is coming out of the board. R is, if I were to associate a position vector to this, R will be radial, and velocity is tangential. And the dipole moment or magnetic dipole moment is coming out of the board. And you notice that R cross V, at least in the directional orthogonality sense, that's equal to n hat. So instead of n hat, I will write this as half times q times position crossed with velocity v. Let me do some more. I'll divide by mass m, and we have q times r cross mv. And what is the cross product of position and mv? Mv is momentum.
Angular momentum.
Right? Angular momentum. So it seems like, so what we are claiming is, for a single point charge at the very basic level, magnetic moment of a point charge now is equal to q over 2m times the angular momentum of that particular charge. Correct? So think of an atom. You have an electron moving around in the atom. Simply because it's moving in a circle, it has an angular momentum. That means the motion of an electron in an atom contributes to a magnetic dipole moment. Any charge moving in a circle will contribute to a magnetic dipole moment, and electrons are a big contributors to that. So most of the atoms, even most of the charged particle alone, they have magnetic dipole moment. Okay. So that's again, in quantum mechanics, this takes a big role in the sense that like Heisenberg uncertainty relation is the basic statement of quantum mechanics. Position and momentum do not commute, and angular momentum does not commute in quantum mechanics. If you guys have some experience with quantum mechanics, Lx comma Ly, right, like position and momentum does not contribute, the x component of angular momentum and the y component of angular momentum is behaves like operators. In fact, that gives you IH bar times Lz. Right? That gives you the z component of the angular momentum. If angular momentum is directly related to the magnetic moment, that means you can measure the magnetic moment, right? If you put a magnetic field to it, there will be interesting things. Any quantum effect is very easy to see using magnetic moment. So the first experiment that was actually done or which directly observed quantum mechanical statements was Stern-Gerlach experiment, where silver atoms were, you created a beam and then it was put into a magnetic field and how it behaved. And that discussed this point. But we won't get into the details in there. So, so there is a quiz, right? So that's a place where I can relegate it to the quiz. Look up Stern-Gerlach experiment. And what is the role of magnetic dipole moment in Stern-Gerlach setup? Okay. So that's an experiment. That was the first experiment to actually detect quantum mechanical or direct observation of quantum mechanical effects. Okay, so that's magnetic dipole moment. One more thing I was thinking. Yes, we just now said that a single point charge has a magnetic dipole moment. What about a single point charge? Does it have an electric dipole moment? In the sense that, remember, if you have a spherical object, right? So this, positive, 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 negative. So if the distribution is not uniform, like you can clearly see that there is more charge onto the top, less, there is a polarization of the charges on the surface of a sphere. That creates a dipole moment. Okay. Now think of an electron. How do we know that the electron is not charged like this? How do we know that it's spherically symmetric? We don't know actually. Okay. So think of an electron, which is the smallest charged particle we know as of today. It is about 10 raised to minus 18 meters. Nothing has been explored beyond that. So to our best guess, or to our understanding, electron is smaller than that. For all you know, it might be 10 raised to minus 30. We don't know. But it's surely smaller than 10 raised to minus 17 meters, 17 or 18 meters. Now, since we don't know anything about the structure of the electron, we can ask, maybe the electron is not spherically symmetric. It is slightly off. It is small sphere, but it is actually polarized. The charges are polarized on it in such a way that it is not uniformly charged. What that would mean is that electron has an electric dipole moment, correct? But as of today, in all the experiments that has been measured, its electric dipole moment is exactly 0. Okay, significantly, it has been shown that it is equal to 0. And there are big consequences if there is any experiment that tomorrow does find out that electron has a electric dipole moment, not a magnetic dipole moment. I'm talking about an electric dipole moment. The fundamental theories that are built on, that are based on, for example, string theory. And have you guys heard of what is called supersymmetry? Like that's again a theory which, or actually I should say something on that. How many guys know what is a supersymmetry? It's reasonably, have you heard of what is supersymmetry?
Like if it undergoes any translation or rotation or anything, it's always the same.
Tell it again.
Like if it undergoes any sort of transformation, like rotation or reflection, or like basically symmetric about every possible axis, would just be a guess. I don't know. For sure.
No, more than that. Anyone else aware of supersymmetry? No? Okay, surprised. By the way, before that, are you guys aware of what is a fermion and a boson? Yes, no?
Say that again.
What is a fermion and what is a boson?
I know they're both particles.
Yes, they are particles. That's correct. Now, okay, good. So this is all comes in what is called particle physics, but just as a general knowledge, it is good to know these things. Now, all the particles that we know about, like at a very basic level, if you think of it as a building block, there are electrons, protons, neutrons. Those are 3 basic ones, right? What else can you think of? There are if you want, there are quarks, there are Higgs, there are about 20 to 30 fundamental particles. But let's stick to electrons, protons, and neutrons. Like even the protons and neutrons are actually built out of quarks. Now, all these particles have very interesting feature that let's say you have two electrons, one in my right hand and one in my left hand. Okay, but I don't open it and show you. In fact, if you see an electron today, it goes out of the room, then comes back to you. Would you ever know that this is the same electron or another electron? Right? Based on looking at it, it will look exactly like a charge, right? Now, here is the question you can ask. Suppose I have two electrons, one in my left hand and right hand, and you do an experiment in the same room. And now I swap the two electrons. I take the electron from here and put it in my right hand, basically swap the electrons, and then ask the question, is there an experiment that can actually sense the difference? Okay. And the point is, yes, electrons are antisymmetric under swap. Many other particles are not. For example, photon are not sensitive to swapping. If you replace a photon with respect to each other, you'll never know. So particles that are not sensitive to swapping, that's called boson. And particles that are sensitive to swapping, that's called fermions. If you remember in your hydrogen atom at the ground state, there are two electrons that you can put in, right? Why two? Why not three? Why not four? If it's a minimum energy, everything should come down, right? Everything should be in the ground state, because electrons don't like to be next to each other. They don't like alike charges. So the best you can have it is that one can have an opposite spin, and then they are of different kind, and that is the best you can do. So that's a basic idea of Pauli exclusion principle, or there is a whole statistics you can build on this. So this is called fermion statistics and boson statistics. So if you were to have an electron and another particle which will cancel this sensitivity, then you can have a lot of particles in the ground state, and that's what is called a Bose condensate. But let me not go beyond that. So the basic idea is, if there is a fermion, it's static, it is not sensitive to swapping, and bosons are fine, they don't care. Like everything remains the same. You cannot do an experiment where you can sense a change. So that's boson and fermions. Is that clear? Any very simplistically speaking? That's simple statistics. Now, what is supersymmetry? This has not been verified yet. In about 1970s, there was a proposition that every particle has a partner associated with it. That means to say that if you have an electron in this universe, or if you are allowed to have electrons in this universe, there exists a particle which is a boson, but having the same mass, everything else is the same, but it's a boson. Like fermion, remember, is electron is a fermion. So you call it S electron. So electron has what is called S electron. So this is supersymmetric electron. Like that's its partner. Right? If you have a photon, so photon is a boson, remember. So these are partners. So you have a photon. So if you have a boson, you will call it a photino. Photino, right? So whenever it's a boson, you will add a O to it. If it's a fermion, you will add an S in front of it. Right? But as of today, we haven't seen any supersymmetric particle yet. And string theory, which probably you have heard of, most of you guys must have heard of what is string theory. String theory depends on supersymmetry. So if you tomorrow find that electron has a electric dipole moment, that would mean that supersymmetry, it violates supersymmetry then. And that would actually take down a very basic pillar on which string theory is based on. Right? So in that sense, supersymmetry is very important, and supersymmetry, it depends or has this prediction that electron is having no electric dipole moment. So in that sense, measurement of electric dipole moment plays an important role, right? But yeah, look up what is supersymmetry. Yeah, how about that? Like, so that can be a quiz. So 2 quizzes, right? One is Stern-Kerr, and the other is what is supersymmetry? Yeah, simple at a very basic, simplistic level. Don't have to get into the math associated with it. Okay, so we want to talk about magnetic dipole moment. And as we pointed out, it is actually associated with the basic circular loop of a wire, right? So current carrying loop of wire, let's say this is Z axis. And what I'm going to do further is that I will have magnetic dipole moment, remember, is n hat times I times A, correct? If you have a loop of current carrying wire. Like in the case of point electric dipole moment, I can say I tends to infinity and A tends to 0. Right? The area of this loop gets smaller and smaller. That means the radius of this loop is made really tiny, in fact 0. But if I say it is 0, then you would say, oh, it doesn't exist at all, so magnetic dipole moment is gone. But I want to balance that 0 by increasing the current in such a way that this remains finite. So these, sorry, I said it wrong, right? This is infinity. I meant to say this is infinity, this is 0, in such a way that they don't, they neither go to 0, they neither go to infinity. I times A is fixed. And that's called, then you don't associate any current to it. There is no area associated with it. Then you just have a pure point magnetic dipole moment. So this is called a point magnetic dipole moment. Now that's of course an idealization. You probably don't have point electric dipole moments, but how can we realize this in nature? Think of the following situation. So this is a loop that is an vector, sorry, there is a radius A associated with it. And let's have the observation point R, right? That's the observation point R, which has the length R associated with it. If A is very much less than R, right? In fact, R itself will be built out of 2 directions, right? There is a Z and there is a rho, right? So we can also say A has to be very much less than rho and A has to be very much less than Z, right? So all 3 satisfied together, okay? In that case, that's a pretty good approximation of a point dipole moment. Okay, and this itself will be called a far field approximation. So far field means we are not close to the wire, we are basically far away. How far? If your experiments has to be done in 10% accuracy, if the loop of the wire is 1 centimeter, you have to be 10 centimeter away. If you want a 1% accuracy, then if this is 1 centimeter, you have to go 100 centimeters away. If it is really a precise precision, high precision experiment, then you go farther and farther and you can make the accuracy better and better. So to 10% accuracy, if you're 10 centimeter away, this is a point dipole, that's it, right? So that's good enough. So how does this approximation work? So let's do this a little bit more. We have 6 minutes, correct? So let's consider this particular wire and ask what is its current density. Current density, we did this last time, is equal to, it is circular, right? So it is phi prime hat, and there is a current I going through it, right? That's the direction of the current. That's the magnitude of the current. And then you also need per unit area. Like that's a cross section of this wire. It is really thin wire. Its cross section is decided by where you're on the z-axis. So that's z minus 0, let's say, right? You're on the xy plane, right? So sorry, z prime has to be equal to 0. And its radius, right? It's basically the cross section of the wire, right? If you think of this wire to be rectangular in nature, it has a small height. The wire has a small height, and it has, in the radial direction, it also has a width associated with it, and that is at rho prime is equal to a. Right? That's a tiny. So if you want to think of it, so this is the wire. And think of this wire to have a small width associated with it, right? So that's z, and that's rho prime at rho prime equal to a. That's your area associated with it. What about the vector potential? That's equal to mu naught over 4 pi times d cube r prime. And you have j of r prime, and that is r minus r prime. Right? That's our simple way of calculating the magnetic vector potential. But in our far field approximation, what's the advantage we gain? We attempted this last time, and we already said that this is going to be hard. So we said, okay, we will calculate it on the axis. Like that was too simple a calculation. But now we are going to go very far, right? So what happens is that if we are very far, r minus r prime magnitude is basically square root of, in cylindrical coordinates, z minus z prime square plus, so z coordinate and x and y coordinates, but instead let me say x and y coordinate is rho minus rho prime square. Right. So this is the perpendicular component of the vector. So z and a vector in the x and y plane. In the x and y plane, in terms of rho and rho prime, this is the same as rho square. I square this plus rho prime square minus 2 rho prime. This is the dot product of rho and rho prime. So it is not just the magnitude, there is an angle between them also that comes in. So that's cosine. Am I within the space? There you go. And there is a square root. Now, what is the advantage of this far field approximation? What we have is z prime is equal to 0, and rho prime is actually equal to a, right? If you are on the wire, that's your source, right? Source is rho prime, that's equal to a. If this is a square, rho square is very large. We are saying that the observation point is very large. or very far away, that means I can neglect this. In fact, I can even neglect this part as far as it is coming together with this, and it is coming together with this. There is an A here, and there is a rho square there. Right? So there's a rho times A and a rho square. So I can actually neglect that also, but if I neglect that, everything will go away. So I want to keep the leading term. So I'll keep this, but I will take it to the numerator. I'll expand this in the powers of A. And that will actually allow us to do it. And we will actually come back and work on that next time, probably on Monday. Or I'll think of what is a problem I can give in the exam also, maybe something related to this. Okay. So again, exam will be homework based. It is more than assessment. It will be to expose you to things, to teach you basically. Okay. Like I'm taking a little liberty here in the sense that first semester I have assessed you guys. The second semester, this is mostly you want to cover stuff. Okay. Okay. That's all. Any questions, comments? Otherwise, thank you.
Thank you.
Yeah, before class, I was just I was just trying to say thanks for sending the Mathematica file. I realized I didn't email you back after that one. I meant to. I guess I just never actually got around to sending one. But I was looking at it. It seemed pretty simple to figure out. I mean, it took me a minute to look through the